So, atomic theory is actually a really old subject, okay? And it's the theory, it's the theoretical understanding that's going to take us from what we've been learning about, which is the macroscopic world, that is the visible world, stuff we can see with our eyes, okay, and feel and hear, etc., to things that are so small, we can't even see them with a light microscope. So the microscope you might have used in Mr. Newman's room, not good enough to see atoms, right? But what are atoms? What are they composed of? And what in the world is the periodic table, and how does that tell us about atoms or elements, or who knows what that is, right? Those are all the things we're going to be studying now. So our topic is atomic theory. And atomic theory dates way back, okay, to like back in the day. So if I say back in the day, what does back in the day mean? Give me a year that might be back in the day. 1750 when?
1807.
1807 when?
1950.
1950, right? So sure, that's back in the day. But we're gonna go way back, right? And we're gonna go back to about 400 BC, okay? Give or take 100 years, right? And that's when the early Greek philosophers, people like Democritus and Plato and Aristotle, Socrates, when all these guys were trying to figure out what the world around them was made out of. So long before the sort of like the technology that was going to be necessary to ultimately flesh out the story of the atom and atomic theory was available, these guys were just with their minds like trying to theorize how the world should be structured. And they got startlingly close, okay? So back in the day, they thought about this concept of divisibility or indivisibility, right? So like, if you take a stick of butter, right, and you cut it in half, what do you have? Half what? Half a stick of butter, right? Okay, then you cut the half of a stick of butter in half, and what do you have? You got a quarter stick of what? Okay, so their question was, to what extent, like, could you keep cutting something into smaller and smaller parts before you would get to that little tiny piece, right, or that little tiny entity that was the indivisible part of that thing, right? So like, how much could you cut it down, or like to what like really tiny, almost infinitesimally small size could you cut something down until it just wouldn't be itself anymore, right? Or until you got to the point at which if you cut again, it would no longer be what it was, right? So what was the smallest, little, tiniest component of whatever you were dealing with? And so this word, atomic theory, that has its origins in the Greek atomos, which is Greek, okay, for indivisible. All right, indivisible. So that's where this theory of the atom comes from. What's the smallest thing you can have that's not divisible anymore, or at the very least not breakable, such that you would still retain all the properties of this thing you'd originally broken down, right? And so that's where it comes from. And we'll come back to this theory because it's not necessarily a theory that you would only apply to atoms, right? You could apply this to other chemical entities too. This theory of indivisible without losing its identity. But atoms are the smallest components of chemicals. Okay? They're the smallest components of chemicals. But what's really interesting is that there are subatomic particles. And so atoms are made of subatomic particles which we don't think about too much when we're thinking about chemicals, okay? We don't think about the subatomic particles as much as we think about the atoms themselves. And so that's why it's okay to think of atoms as being the smallest components of chemicals. That's okay, all right? But you do have to know that atoms are made of subatomic particles. And those particles are the protons, the neutrons, and the electrons, yeah? Okay? And I'm going to put the little E minus symbol there because I don't want to mess up my panel, but I'll spell electron in a minute. And so now we need to talk about the subatomic particles. So Terrell, your hand's no longer raised. Did I answer your question?
Oh no, I was gonna ask, can you physically cut something to like atomic level?
Yeah.
Again?
Yeah, people, there are ways to do that. There are ways to isolate individual atoms, yeah.
Oh.
But to be honest with you, I'm not that familiar with them. But yep, that can be done. So subatomic particles are the proton, the neutron, and the electron. We need to understand them, right? So I'll write a little table here. So particle, mass, and the unit is AMU, and then charge. So protons have a mass of 1 AMU and a charge of +1. Neutrons have also a mass of 1 AMU. Intriguingly, they are neutrally charged. So they have a charge of 0. Okay? No charge. Electrons, and I'll leave my spelling consistent. So proton, neutron, electron. The electrons have a mass of 0 AMU. Okay? If you ask a particle physicist what the mass of an electron is, the particle physicist can tell you because the particle physicist cares about the mass of an electron. The chemist doesn't, okay? For all chemical purposes that I've ever encountered, I have not needed to know the mass of an electron. And so I can look it up, and I can tell you that an electron does have a mass, but it's so small compared to the mass of the neutron and the proton that for all chemical purposes, we consider it 0. So just remember that the mass of an electron is 0, okay? Is it actually totally? No, it's not. It's not actually totally 0, but the best approximation for all of our purposes will be 0, yeah.
Can the charge on a particle be larger than 1?
No, these charges are whole number charges. So we've got +1 and -1. And for these particles, protons are always charged +1, electrons are always charged -1. Now there are other things, okay, other kinds of particles that are not subatomic particles that can have charges that are not +1 or -1. But for the subatomic particles, we're limited to these numbers. +1, -1, and 0. Okay? Good questions. All right, so these subatomic particles make up atoms. And atoms are of one type of element or another type. And all of our elements are represented in the periodic table of the elements. So everybody in here is going to get one of these. Okay, we're not there yet quite, but you're going to get one of these. And when you do, and there's one on the board back there, if you want to look at it, okay, when you do, you'll find that the smallest element is this guy right here. Hydrogen. Hydrogen has this number written on top, 1, and then on the bottom it has roughly 1.01. Okay, what's going on there? What's going on?
It has
So-
one charge, and then it has...
I got this.
Oh, I thought you were asking.
So, this number here is the atomic number. Okay? Atomic number. And that's the number of protons. Okay? So the atomic number is the number of protons. So hydrogen has how many protons? 1. 1 proton per hydrogen atom. Okay? 1 proton per hydrogen atom. this is the atomic symbol. Which implies the name of the element. Okay? H stands for hydrogen. In some periodic tables, hydrogen will be fully spelled out. In other periodic tables, it won't. Okay? You'll just have an H. So the atomic symbol tells you what the atom is. Okay? What's the identity, what the name of the element is. And then down here we have the mass number. Okay? And this equals number of protons plus number of neutrons. And I'll abbreviate neutrons. Okay? So the number of protons plus the number of neutrons. Leslie, go ahead.
So if you wanted to know how many neutrons there are, you would just subtract 3.
So that's where we're going. So what we want to be able to do is diagram what an atom of hydrogen looks like. So how are we going to do that? Well, we start out with the atomic number. How many protons does hydrogen have? How many? 1, right? And then what's the charge on a proton? Plus 1. So we represent that proton with a little plus sign like that. We put a circle around it. That means we've got a proton. And one thing that you need to know is that the protons and the neutrons are also called nucleons. Nucleons. N-U-C-L-E-O-N-S. Nucleons. Why are they called nucleons? They're called nucleons because they're located where within the atom? Nucleus. Good. Okay? So the proton here is in the center of the atom, the nucleus. And we'll be learning more about the nucleus. But for now, we've got 1 proton, and then you got to do your math here, just like Leslie was saying. So 1 proton plus X neutrons gives us right around an atomic mass of 1, right? So how many neutrons do we need to go from 1 to 1? Do we need a neutron? Neutrons have a mass of 1. 1 plus X equals 1. What's X? 0, right? If 1 plus X equals 1, X is 0. So we need no neutrons here for hydrogen, okay? Hydrogen generally doesn't have neutrons. Why is there a 0.01? Because a really small percentage of hydrogen atoms has a neutron, okay? Really small percentage. This is an average atomic mass. It's not an atomic mass for any one particular type of hydrogen atom, those are called isotopes. We'll talk about that later, okay? But we're going to be comfortable just rounding that down. So you've got, in the vast majority of hydrogen atoms, 1 proton. You've also got to have balanced charges. So if we've got a proton in the nucleus, we've got to balance its charge. Well, which subatomic particle can balance the charge of a proton? Okay, the electron has a charge of -1. That can balance out the charge +1 from the protons. Okay? So if we're going to make this atom, and all atoms in the periodic table are considered electrically neutral. So if we're going to make it neutral, how many electrons do we need to balance out the charge of this proton? 1. We're going to draw that out here. And we're going to say some things that are really important. This circle indicates an energy shell. Okay? So this is an energy shell. Shell or level. Not a circular orbit. Okay? That's what that is. And then this guy right here exists in a spherical cloud around the nucleus. And this one can actually exist at the nucleus. So this electron can be right there in the nucleus, and then it can just fly off. It's gonna occupy a spherical cloud around the nucleus. Okay? Leslie?
What do you mean by spherical?
Spherical means round, like a ball. A ball is a sphere.
So the electrons, it can go anywhere?
It can go anywhere, okay? It can actually be anywhere in the universe, but the most likely spot is actually at the nucleus. So a good way to think of it is like a boba ball, okay? You go to your Asian dessert store and you order your smoothie or your tea with boba, right?
Yeah.
And you get your little boba ball, and the boba ball on the outside is kind of soft, right? But as you bite into the boba ball, what do you notice? It's a little more chewy, right? So there's more likelihood that the electron will be right in the middle, but it can also be toward the periphery, okay? There's more electron density, we say, near the nucleus for this kind of an electron arrangement. We'll get into all of that later on. Okay. So hydrogen can be diagrammed like this. Well, what about larger atoms? What about helium, which has an atomic number of 2 and a mass